It looks like nothing, just gray, lifeless powder spread across a silent world. Regolith, the fragmented remains of billions of years of impacts, covers the moon and countless asteroids in layers meters deep. It coats asteroids, it blankets moons, it drifts across worlds that have never known wind or rain. But what appears useless may become the foundation of something extraordinary. Using advanced 3D printing technologies, this simple dust can be fused and shaped into solid structures. Landing pads to prevent dangerous dust clouds, radiation shields thick enough to block cosmic rays, protective walls built from the very ground beneath our feet. Entire habitats could rise from lunar soil, reducing the need to launch heavy construction materials from Earth's gravity well. In space, even dust becomes infrastructure, and the most abundant material in the solar system may become the backbone of human expansion beyond Earth. On Earth, energy has always come at a cost. Fossil fuels scar landscapes, nuclear power leaves behind long-lived waste, and cleaner sources still struggle to meet global demand. Helium-3 is extraordinarily rare on our planet. Only trace amounts exist naturally, too little to power a civilization. But over billions of years, the solar wind has implanted this isotope into lunar soil, leaving reserves far greater than anything found on Earth. Helium-3 is often described as the fuel of future nuclear fusion, a process that mirrors the energy of the stars. If fusion becomes commercially viable, helium-3 reactions could produce immense energy with minimal radioactive waste, cleaner, safer, and extraordinarily powerful. To access it, lunar regolith would need to be heated and processed, extracting minute concentrations from vast amounts of soil. The journey from lunar surface to Earth orbit is far easier than launching from our planet's deep gravity well. If harnessed responsibly, the moon may one day power the world below, transforming energy markets, reshaping geopolitics, and redefining humanity's relationship with the cosmos. But fusion remains one of the greatest engineering challenges in modern science. The promise is immense, yet still unproven at scale. Between Earth and Moon lies more than distance. It is a bridge between scarcity and abundance, and perhaps the next chapter in humanity's search for power. Lightweight, durable, resistant to corrosion, aluminum has shaped the age of aviation and the rise of modern transportation. But every spacecraft we build today must escape Earth's gravity, carrying not only its mission, but the immense cost of launch. Gravity demands energy, energy demands fuel, and fuel demands weight. It is a cycle that makes spaceflight expensive and limiting. Yet aluminum is abundant in lunar soil, locked within regolith, waiting to be extracted and refined. Through advanced processing techniques, this common element could be separated and transformed into structural-grade metal, without ever leaving the moon. In orbit, where gravity is nearly absent, massive structures can be assembled with far less energy than launching them fully built from Earth. Instead of launching complete ships from Earth, we may construct them piece by piece in space, using materials sourced beyond our planet. Aluminum built the aircraft of the 20th century. In the centuries ahead, it may build the vessels that carry humanity beyond Earth, not from the ground up, but from orbit outward. Modern civilization runs on something almost invisible, a material so common we rarely think about it, yet so essential that without it, our world would fall silent. Silicon forms the backbone of modern technology, microchips, processors, the circuitry that powers communication, computation, and control. It is also the foundation of solar panels, converting sunlight into electricity on rooftops, in deserts, and across power grids worldwide. Yet silicon production depends on complex global supply chains, mining, refining, fabrication, concentrated in limited regions of Earth. But silicon is not rare in the solar system. It exists abundantly in lunar regolith and in countless asteroids drifting beyond our atmosphere. Mining and processing silicon in space could enable orbital manufacturing, building structures where gravity is minimal and launch costs are reduced. Gigantic solar farms in orbit could collect uninterrupted sunlight, free from night cycles and atmospheric interference. Off-world manufacturing would reduce the need to launch finished products from Earth, shifting industry beyond our planet's surface. As infrastructure expands into orbit, dependence on fragile terrestrial supply chains may begin to ease. Silicon built our digital age on Earth. In space, it may help build something even larger, an economy no longer bound to a single world. Some materials shape civilization quietly, not as fuel, not as energy, but as strength woven into the structures that carry us forward. Magnesium strengthens the alloys used in aerospace engineering, reducing weight while maintaining structural integrity. In spaceflight, every kilogram matters. Less weight means less fuel means greater range. And like aluminum, magnesium exists within lunar regolith, embedded in the same dust that blankets the moon. Extracted and refined on-site, it could become a critical ingredient in space-based manufacturing. Lightweight magnesium alloys could support long-duration missions, spacecraft built not for orbit, but for deep space. The farther humanity travels, the more essential such materials become, not optional, but necessary. In the vacuum beyond Earth, strength is survival, and in the quiet dust of the moon, the elements of that strength already wait.